Hello, myself Priyanka Katare, Assistant Professor in Department of Electronics Engineering, Walchand Institute of Technology, Solapur. Today in this video session, we are going to see one of the important technique in the artificial intelligence, that is the constraint propagation. After completion of this session, student will be learn how constraint propagation is applied to solve the CSP, that is the constraint satisfaction problem. Gain insight into the iterative process of constraint propagation through an example of the map coloring problem. Appreciate the efficiency gain achieved by the constraint propagation, narrowing down the search space and finding the solution. So in this whole session we are going to see these points, that is introduction of the constraint propagation, constraint satisfaction problem, overview, example using that map coloring problem, constraint propagation process, iterative constraint propagation, result of the constraint propagation and benefits of these techniques. So what is actually constraint propagation? Here, just like a algorithm previous search techniques, this is also using some search technique also, but here there is, while assigning some value to particular any domain, we are checking some condition also. So here some one or multiple conditions, or we can say constraints, are involved in the technique, so it is called the constraint propagation. This technique is used to solve some basic artificial intelligence problem which are called the constraint satisfaction problem. Constraint propagation involves iteratively, we are iteratively applying constraint at every iteration for checking the variables. It is a fundamental method efficiency solving the CSP problems. But what is this constraint satisfaction problem? Okay, we know that for doing any task, there are some multiple variables are there, multiple domains are there. Okay, but what is variable? Variables are entities whose values we need to be assigned to the particular domains. Okay, domains are sets of possible values or variables. Okay, these are the, for example, we know that suppose we are making the timetable or schedule for any program. Suppose we are making schedule or timetable of for the particular class, then the periods, or we can say there is 1 hour by hour periods are there. These periods are called the actual the variables are there. And domains means what? The multiple subjects are there, which subject we want to allocate for that particular period. This subject and those teacher are called the, we can say, domains for that particular variable. And constraint means what? The constraint just we are checking while assigning any domains to particular variable. While assigning, before assigning, we want to check whether that condition or constraint is satisfying or not. So that is called the constraint satisfaction problem. Its example, that is map coloring problem. So it is one problem where that map, their particular nodes are present, okay, and we want to color each and every node in that graph. But before assigning color, we want to check there no any adjacent node have the same color. Means what? Adjacent node should have the different color we want to assign them. So we are checking that condition in while assigning each and every color assignment. Means we are iteratively checking the constraints. So these such problems are called the constraint satisfaction problem. Just we have seen the time schedule or timetable making problem, or this color mapping problem. These are the example of the constraint satisfaction problem. Iterative constraint propagation. So it's identify first. It's identify uncolored region and their neighbors. Okay, here what at every iteration what we are doing, we are just identifying at the whole map which is the region that is we have not assigned color, or we can say the uncolored region, and its neighbors, whatever its neighbors, how many neighbors are there, just we are looking in every step and eliminating the color. Suppose it neighbor have already colored, and that color we are avoiding, or we are eliminating the colors which have already assigned to its neighbors. So demonstrate how this process constraint propagation is repeated iteratively. So here iteratively we are just checking for any region it is not colored, means we are assigning color, and before that we are checking condition whether its neighbors have same color or not. So here it is very efficient because we are iteratively doing the same process. It is an example of the map coloring problem. So here in this figure we can see there is the uncolored map is there. So in this map there is 4 nodes are there. So these nodes we can say the variables are there. Just 1, 2, 3, 4 these sets are our variable. Initially there is not given assigned any color to these nodes. So what is constraint here, that adjacent region must have the different colors. Suppose there is 1 is connected to second node, means this 1 and second both have the different color, they should not have the same color. A limited set of colors are available, means there are some limited 3 colors we are using while solving this problem. So this is actual initial state of our map. So here just we are starting from the initial state. Iteratively we are applying constraint to reduce the domain of the possible initial domain. What is the initial domain for each node? That all the 3 colors, actually red, green and blue. Initially there is all the nodes are uncolored, means at every node we can assign any color from these 3 nodes. So it continue until solution will get that all region we are assigning all the color. Here what is variable? That set of 1, 2, 3, 4 this is the variable. And what is domain? That is RGB, that is the available color. Red, green and blue are the available color are here. And what is our condition? That neighbor node, that 1 and 2 are should not same, 1 and 3 should not same, 1 and 4 also should not same, 2, 4 also should not same, and 3, 4 also should not same. Whichever the adjacent node, they have different color are there. So in the next step what we are doing, just we have assigned our initial node, that is first node, we have assigned our any random color. Just suppose we have here in this example we have assigned red color to the first node. So just we are checking for domain of the remaining node. We can see one node is connected to 2 and 3rd. So we can see in the domain of second and third node only green and blue color are there. And 4th node is also connected to this first, means that all 3 have just we can assign one of the green and blue color. So in the next step to the second node we have assigned green color, and remaining 3rd and 4th now domain is, we can see that second node is connected to only 4th node. First node is already colored, which is uncolored, that is 4th node which is adjacent to 2. So now 4th have only single color in its domain, and 3rd node have green and blue color in its domain. In the 3rd step just we have assigned blue color to the 3rd node, that is now we can see first node is red, second is green, 3rd is blue, and 4th only first one single color is remained, that is called the genuine color. There is no any other option for this 4th node. So by default we have assigned blue color to the 4th node, but we can see in the graph also and in the table also 3 and 4 we have assigned same color. So this is called the dead end. So I want to ask you one question. What is constraint satisfaction? Means whatever constraint are given in that problem, that should be satisfied in every decision. Whatever decision we are taking there while assigning any color, the condition should satisfy there. Okay, that is called the constraint satisfaction. But if at any iteration both the neighbors have same color, what to do? So there is one solution, that is the backtracking in the constraint propagation. So in the backtracking, it is a technique used in this propagation that efficiently explore the search space when constraint lead to the dead end. When such type of problem occurs like this, okay, where we can see the neighbors we have assigned same color, in such problems we are using backtracking. Just we are backtracking means we are reached to the state where we can see where due to that decision the dead end is occurred, that decision we want to change. This process is called the backtracking. It avoids the unnecessary exploration of the invalid solution which will reach to the dead end. So what is the decision here, due to which decision, that due to that here, due to that 3 equal to g actual problem occurred. So in the next step what we are doing here, we have changed that decision, that instead of blue color, to the third node we have assigned green color. So we can see in the diagram, after assigning green color to the third node, we can assign now blue color to the fourth node. So all the nodes are now colored, and you can see there is no any, all the conditions are satisfied, because every adjacent node has different color. 1 2 have also different color, 1 3 have also different color, 3 4 2 4 and 1 4, all adjacent node are have a different color. So this is the result of our constraint propagation. So what is benefits of this propagation? It efficiently narrows down the search space, facilitate the discovery of valid solutions, and enables systematic exploration of the possible combinations. These are the references used for while making this presentation of this session. Thank you.